so this is problem number 4 on set 5. And I'm not going to copy the text of it, but I'll read it out loud. This is the picture. It says, a semicircular slot, so here's the semicircular slot of 10-inch radius, r equals 10 inches, is cut in a flat plate which rotates about the vertical AD at a constant rate of 14 radians per second. Okay, I didn't put that. So omega equals 14 radians per second, and it's constant. A small 0.8-pound block, E, is designed to slide in the slot as the plate rotates. By the way, did anybody notice that the picture for this problem was a little bit weird, and that the way they showed it physically didn't make sense? Because they show the slot, but then they show the little block at E kind of like a pin on a rod, which doesn't make sense if this slot is cut anyway. So it actually had to look, so my picture is slightly different than the picture in that problem, but the picture in the problem didn't really make sense. So it's more like that. Okay, so a small 0.8-pound block E is designed to slide in the slot as the plate rotates. Knowing that the coefficients of static friction are 0.35, kinetic friction is 0.25, we want to determine, in other words, find whether the block will slide. Will the block slide? If it's released in a position corresponding to theta is 40 or theta is 80. And so actually one of the answers is yes and the other answer is no. Also, they want us to determine the magnitude and direction of the friction force exerted on the block immediately after it's released. So we also want to find friction force. All right, so, I do want you to do this on the test. The way professional engineers lay out their problems is they have a section for all the given information, and then they have a section that clearly identifies what it is you're being asked to find, and then we'll start the solution and label that as well. Okay, and I always like to go back and make sure that I've got all the given information on my paper. So I'm just going to read it real quickly again. Semicircular slot, 10 inches, cut in a flat plate, rotates about the vertical at a constant rate of 14 radians per second. Small 0.8-pound block is designed to slide in the slot as the plate rotates. Coefficients of friction are mu s 0.35, mu k 0.25. Determine whether the block will slide if it's released in the position corresponding to theta 40, theta 80, and also determine the friction force. Okay, so, any ideas?
Free body diagram.
Good. When in doubt, do a free body diagram. That's a great idea. The other thing is, if we assume that it doesn't slide, it simplifies the problem greatly. Because if it doesn't slide, then the motion of this block E is simply a circle around the axis AD. And so we know the path of motion, and because of what I said earlier, once we know the path of motion, the correct, easiest coordinate system that you should use on this problem would be the normal and tangential. So, but I better state that assumption. So if we assume that the block does not slide, and by the way, if it doesn't slide, then what that means is that we've got static friction acting on it, and we know that there's a limit to how big the value of that static friction can be. So that's what we have to check at the end of the problem. And we are asked to find the frictional force anyway. We've got to make sure that this frictional force does not exceed the allowable frictional force. And then if it doesn't, then we'll say that our assumption was right, and if it does, we'll say our assumption was wrong. If our assumption was right, then we answer the question no. And if our assumption is wrong, we'll answer this question yes. Okay, so that's the strategy here. All right, so let's assume the block does not slide. So therefore, so then block has circular path. And let's draw the free body diagram. Okay, so I'll draw the free body diagram and set it equal to the inertia vector diagram. So this is how I'm going to tell my teacher the method that I've chosen. I'll just write down the equation F equals ma. So I know which method you've chosen. If you write down, well, you can actually write down the words work energy theorem, or you could actually just put the formula for the work energy theorem, and same for principle of impulse and momentum. All right, so let's see. So I drew the body. Now I've got to think about all of the forces acting on this body. Well, the easiest one to think about is mg. Oh, maybe I should draw the, you know, by the way, people go sometimes a little bit nuts with all the colors. The only thing that I want in green is the body. The only thing that I want in pink are the forces. And then on this one, the body would be in green, and it wouldn't be forces in this one, it would be those acceleration vectors, right, times m, so it would be the inertia vectors. So that's all I want in pink and green. Everything else should go in your pencil color. Okay, so let's see. If this thing is rotating like this, then the normal direction, I'll just show the normal vector would be like that, right? And the tangential vector would be tangent to the path, which would be basically perpendicular to the board, right? Coming out at you. You know, like if you think about this coming this, like in the position here that it's coming at you. That's the way I'm showing it.
So it feels good the other way, you do an X?
Yeah,
That would be...
but you know, and it really wouldn't make any difference except that I don't want to deviate from what I have on my paper, so, and I show it like that on my paper. So those are, and then where's the binormal?
Perpendicular to the cross of those two?
Right, so it's ET times EN. Okay, there you go. Okay, so the weight is basically in the binormal direction. Okay, and then, all right, so when you do a free body diagram, this is what you always think about the gravitational force. You know, there wasn't any problems in the course with a magnetic field, but you should, you know, think of all the possibilities. If there's any electromagnetic forces that might be acting, you should think about those, but there's not. Then the other thing is any contact forces. Okay, so we took away the slot. So we have to represent the forces that the slot are exerting on the block. Okay, and it's a little bit complicated because, you know, this is a three-dimensional problem.
It's on the normal and on
Well, okay, first of all, you should always realize that whenever there are surfaces in contact, which there are, and I'm going to blow this up a little bit just to make it kind of a three-dimensional picture. So you've got the slot. Okay, sort of like that. So this surface here is what's touching the surface of the slot. Okay, it's a surface of contact. Whenever you, okay, and what we've removed, and it's not the best picture, it should be smoother, right? Anyway, what we've removed is the slot. So So we've removed this surface. So what we need to show, and by the way, so this surface that it's acting on, that's basically this plane and edge view here, right? So we've got normal and frictional forces. The normal one is always perpendicular to the surface. The frictional forces are always parallel to the surface.
So normal going on EV and EN direction.
Well, it's normal to the surface.
Yeah.
So,
So it should be normal.
so it would be this.
Normal on EV also, ET also. There's no component on ET. Because ET is moving, right?
I don't really understand what you're asking.
I'm saying that the normal force has no component on tangential.
Sure it does.
Yeah, you can split it up.
Sure it does.
Yes.
Oh wait, no, you're right, because it's perpendicular to
Yeah, it's
it.
perpendicular.
So,
Has only
but
the
there's
component.
frictional forces in
Yeah,
the...
the frictional has two components.
Okay, so would everybody agree that the normal that's odd, is perpendicular to the surface? And of course, you know, it's distributed over the whole surface, but if you add up all of those forces that are perpendicular, you'll just get the one resultant that I'm calling N here.
We still have to consider the top surface that was also.
No, you know, I just considered the bottom.
Okay.
If you did want to consider the top, that would be okay, but it would
still
the
be
top
an
is
N.
parallel to the
Yeah.
bottom, so you could just kind of combine them all into one big resultant that I'm calling N here. The only difference would be is that there would be a possibility that this would be going in the other direction,
Right.
which I'm not really taking into account just because
Yeah, it's
just not likely.
it's not going in ET
Yeah.
because it's like moving frame. ET is
Alright.
always perpendicular.
So,
So
okay, so now I have to address the frictional forces.
this is going to be perpendicular to N.
So, okay, but do you see that the frictional force would be in this whole area? And so
It's against the motion, whatever the motion is.
we could actually break it into two components. One in this direction, and I'm not going to show the arrow, and then one in the ET direction.
I think it's on.
You know, it's getting a little messy, but let me see if I can put it in a position. Here, I think I'm going to do this. Okay, so here's one component of the frictional force, and I'll call that F, and then I'll call this one FT. So between these two, that's the total frictional force.